All right, welcome back. In this portion of the lecture, we're going to be talking about sequential pricing. In particular, we're going to be looking at how well mechanisms that take the following form approximate optimal mechanisms. Uh, Order the agents and post prices to the agents as they arrive in this order. Okay, so we're going to be showing mechanisms of this form are approximately optimal. The main approach that we're going to be taking is to identify a good upper bound on the optimal mechanism, and then to look at pricings that approximate this upper bound. Okay, uh, this upper bound is one of the canonical upper bounds in the literature on Bayesian approximation. Uh, and, and that's the following. So the idea is this. Um, we'd like to design a simple mechanism that approximates the optimal mechanism. And the problem is the optimal mechanism is complex. And so we're unlikely to get a simple understanding of this complex optimal mechanism. And if that's the case, how are we going to show that some simple thing is close to this complex thing? And the idea is, well, let's relax some of the constraints of the optimization problem. Uh, and in doing so, we'll get an upper bound on the optimal performance. But let's relax constraints in a way that if we then solve that relaxed optimization problem, we get a simple solution. Great. And so the relaxation we're going to talk about is called the ex-ante relaxation. What we're going to do is we're going to relax the ex post feasibility constraint that says, for example, if I have a single item auction environment, the ex post feasibility constraint says you can sell at most one item, period, no matter what happens. And we're going to relax it to an ex ante feasibility constraint. And an ex ante feasibility constraint is going to say you can sell one item in expectation over the types that show up. Okay. Great. So a profile of quantiles is going to be ex ante feasible if for each if for each agent their quantile in the profile is equal to the ex ante allocation probability of that agent under some distribution of feasible outcomes. Okay, so give me any distribution of feasible outcomes. I can project that distribution onto the marginal probability that an agent is allocated, and I will get a profile of ex ante allocation probabilities. The space of profiles that I can get from such a projection is the ex ante feasible space. Okay, so here's the straightforward proposition. The optimal ex ante revenue is at least the optimal revenue. And why is this? Well, look, we've just relaxed the feasibility constraints. Okay, so note that every ex post mechanism induces a feasible ex ante profile of probabilities. And therefore, every ex post mechanism is also ex ante feasible. Good, so I want to look at an example just to make sure that we're on the same page. And the example we're going to look at is the single item auction. So what would a profile of allocation probability, ex-ante allocation profiles have to satisfy to be feasible in a single item scenario? Well, it just better be that I don't allocate more than one item in expectation. Okay, in other words, the sum of the allocation probabilities, some of the marginal probabilities I allocate the agents has to be at most one. Great. And so that's going to give us a ex-ante optimization problem, which I can write out as a mathematical program. Okay, and so that program is to maximize over quantile profiles of quantiles the ex ante, basically the revenue that I can get from selling to that agent with probability as given by the profile of quantiles. And notice that that's exactly the revenue curves that we defined previously, right? So the revenue curve is defined as the optimal revenue you can get from selling to an agent with ex ante probability uh, given by a QI hat. And so that's what Ri of QI hat is. Okay, subject to the constraint that these ex-ante allocation probabilities are feasible. So for a single item auction, that would be subject to the constraint that the sum of these ex-ante ex-ante constraints are at most one. Okay, some notes. Um, what does the solution of this program look like? Well, it's going to equate marginal revenues. So at the optimal solution for two agents, I and I prime, the marginal revenues are going to be equal. Furthermore, it's going to decompose across agents. Once I tell you what the allocation probabilities are, the optimal thing you do for that agent is going to be independent across agents. And in particular, it's going to look like a pricing. Okay, so the optimal solution is going to be a pricing, which I'll denote by the vector v hat with components v hat 1 to v hat n. Okay, and here v hat is equal to the value that corresponds to the quantile, the ex-ante constraint qi hat. Great. So that's the ex-ante optimal mechanism. And as I said before, we're hoping to identify an upper bound on the optimal revenue that's somehow simpler. This upper bound on our optimal revenue is in fact a pricing. But as we sort of promised, this pricing is not guaranteed to be ex post feasible. It's only guaranteed to be ex ante feasible, meaning it's going to sell with an expected 1 unit of the item if we had a single item auction constraint. But it may sell more than 1 item given the realizations of the types, because it's going to post prices, and it could be that a couple high types show up and they all buy, and then we're no longer ex post feasible. Great. So now I want to talk about sequential pricing. And in other words, I've got this upper bound from the ex-ante optimal mechanism, which is a pricing. And I'd like to find a pricing that's ex post feasible that's getting close to the same revenue. Uh, and the idea here is simple. Like, look, I've already got a pricing. The problem is it's just not ex post feasible. So why don't we try to resolve the ex post feasibility constraint? And we'll do that by putting the agents in order, offering them these prices, and letting them accept their prices while supplies last. So if we run out of items and it's no longer feasible to serve an agent, then they came too late, too bad. Okay, so we're going to take the optimal prices from the ex-ante relaxation, and we're going to put the agents in order and offer them these prices in order. Okay, and the theorem is that sequential pricing is an e over e minus 1 approximation. E over e minus 1, by the way, is about 1.58. Great. Okay. Right now, we're going to actually prove a simpler version of this result. We're going to show that if the agents are IID, we have a single item to sell, and we have a regular distribution, that sequential pricing is an e over e minus 1 approximation. Okay, so while the theorem holds for matroids, we're going to, and for non-identical distributions, we're going to prove it for IID distributions in a single item, which is a special case of a matroid. Okay, so we're going to have three main steps. We're going to analyze the ex-ante relaxation ref. We're going to analyze the approximation mechanism, sequential pricing, and then we're going to combine to get the desired result. Great. Okay, so uh, we have IID agents. Okay, so IID agents, uh, the ex-ante relaxation is a symmetric optimization problem. We're going to end up offering them all the same price, which is going to sell to them all with the same probability. And with large enough n, this is going to sell to each agent with probability 1 over n. Now, so let's assume that it does. In fact, if it doesn't, then it's even easier to prove this bound, but just for simplification, I'll assume that it's selling to each agent with probably 1 over n. Great, so what is the ex-ante relaxation, the reference mechanism? Okay, so that's gonna sell to each agent with probably 1 over n, and it's gonna offer them the price that corresponds to the quantile 1 over n. And it's going to get that summed over all agents. Well, look, this is symmetric, so there are n of these agents. The quantile, the probability they accept is 1 over n, so n times 1 over n is going to be 1. And the price they offer, the price that we offer them is going to be v of 1 over n, which I'll call v hat. Great. So our ex-ante relaxation in this symmetric situation is getting revenue exactly v hat, the price that we're posting by the ex-ante relaxation. Okay, great. Now we're going to consider sequentially posting a price of v hat to the agents. Okay, that's our approximation mechanism. And what is its revenue? Well, it's going to get revenue v hat when it sells. When does it sell? It sells when there exists an I where the agent's value is at least v hat. Okay, that should be just v hat with no I. Great, so what is the probability that there exists an agent with value at least v hat? Well, it's 1 minus the probability there doesn't exist such an agent. So it's 1 minus the probability all of the agents have value below v hat. Okay, and q hat is the probability they're above v hat. 1 minus q hat is the probability they're below. These agents are all symmetric, so it's going to be v hat times 1 minus q hat to the n. It's the probability that that 1 minus q hat to the n is the probability that they're uh, all below v hat, and then 1 minus that's the probability that it's not the case they're all below v hat. At least one is above v hat. Okay, and of course q hat was 1 over n, so this is 1 minus 1 over n to the n, and this can be upper bounded by 1 minus 1 over e. Okay, using the usual approximation that this is about 1 over e, and in fact the approximation is going in the right direction, so this is in fact a upper bound for all n. Okay, great. And so now we're ready to combine our analysis of the reference mechanism ref, our analysis of the approximation mechanism APX, to determine that the approximation is an e over e minus 1 approximation. Great. Okay, so that's that lemma is a special case of this general theorem. Now what we're going to do is we're going to talk a little bit more about what goes into this general theorem. Okay, and that brings up a topic called correlation gap. And correlation gap is a really, it's an amazing mathematical result. And we're asking the question, I have some objective performance I care about, like revenue, and I'm wondering if correlation really could increase revenue a lot over the case where things were independent. So if we had correlated values, would that be, giving us much more revenue than if we had independent values? And the answer is, under some assumptions, no. And correlation gap sort of says when the answer is no. Okay, so let's jump into how to state the correlation gap question. Okay, so we're going to have a ground set of n elements. You think this corresponds to the bidders we were talking about previously. We're going to have a set function that maps subsets of those elements to real numbers, which are performance, think revenue. And there's going to be a distribution over the ground set. So this is going to be a distribution over the sets of agents that show up. Great. So the correlated value is just going to be the expected value of the set function g when a set is drawn from this distribution f. Okay, great. So the next thing we're going to do is ask what happens if we look at the independent version of the distribution f. Okay, so let's define the marginal probability that any agent I is in this set S as Qi. Okay, so it's the probability we draw a set S from F and that I is in that set. So it's the marginal probability that element I is in the set. Okay, and then I'm going to define the independent distribution F super I just to be the distribution where I is in S independently with probability Qi. Okay, and now I can define the independent value just the same way as I define correlated value. It's just the expectation over sets drawn from the independent distribution of the set function. Great, I'm now ready to state the correlation gap. Okay, so the correlation gap of a set function should be a little g. Is the maximum ratio of the correlated to independent values over correlated distributions f. Okay, so if I have a set function g, or it's the maximum ratio of the correlated distribution to the independent value, correlated to independent value over distributions f. I could also ask what the correlation gap is of a family of functions, and it's just the maximum correlation gap of any of the functions in that family. Okay, so here's the kind of set functions we're going to be looking at. So we'll say G is submodular. This is something that you've undoubtedly seen before, but I'm just going to define it just to be precise. If I have two subsets of the ground set, one contains the other, and I have some element that's not in these sets, then it's submodular if, in some sense, this is some kind of diminishing returns. Okay, if adding that element I to the smaller set has greater marginal benefit than adding it to the bigger set. Okay, so I get more, there's more gains to adding this element to a smaller set than to a bigger set. So we'll say it's submodular. That's true. Okay, and then the theorem is that if the set system is submodular, if the set function is submodular, then the correlation gap is bounded by E over E minus 1. Okay. So what are we saying here? We're saying that if we have a distribution of our subsets that's correlated, and we're evaluating a set function, submodular, we're saying the correlated value that we get, the expected value of this correlated distribution, can't be too much more than if we instead evaluate the independent distribution. The distribution with the same marginals, but with independent. Each element was independently in the set or not. This is a remarkable theorem, and I can't tell you, the surprising places this theorem becomes relevant if you're looking at questions of approximation, because if you don't care about an E over E minus 1 factor, and again, this is about 1.58. If you don't care about an E over E minus 1 factor, and analyzing correlated distributions can be challenging. You can just analyze the independent one instead, right? And the correlated distribution can't be that much more. Okay, so if you wanted an upper bound on the correlated distribution, it's E over E minus 1 times whatever your analysis is of the independent distribution. So this is a theorem that is useful in many surprising places, and one of those places is going to be approximation of posted pricing. Great. So we're going to be applying correlation gap to pricing, and here's the idea. The idea is, when we relaxed feasibility to get ex-ante feasibility, we got outcomes, and the problem was well, look, we're letting the ex-ante relaxation serve two high-valued agents at the same time when we only had one item. So this is sort of infeasible. And another way to look at this is, well, if we allow you to correlate the types of the agents, well, then you can serve two high-valued agents because you correlate them so they don't both show up at the same time. Okay, and so in some sense, the ex-ante relaxation is letting you sort of perfectly correlate things. So, the high-valued people don't all show up when they're infeasible to be served. Okay, so let's make that precise with an example. So let's look at the max weight element set function. Okay, so here I have a bunch of weights, v hat I. Okay, and the max weight element set function given a set S, it finds the v hat I in my set S that has the highest value, and that's its value. Okay, now I'm going to show you that this question of whether sequential pricing is a good approximation of the ex-ante relaxation for single item auctions is equivalent to the correlation gap of the max weight element set system. So that's what we're doing right now. Great. So let's just see how each of these pieces fit together. All right. So the ex-ante relaxation, this is, as we saw, it's just the sum of the probability I allocate times the price I offer, because the ex-ante relaxation is the pricing. And so I'm going to define now a correlated distribution of our subsets of agents. And what I'm going to do is it's going to be the correlated distribution that's perfectly correlated. So exactly one of these agents shows up at once. Okay, so my correlated distribution F is going to be, I will draw the subset S, and the probability that that subset is equal to the singleton I is exactly equal to Qi hat. Okay, well, the sanctity relaxation, probably this Qi hat sum to 1, so there's no probability that any other set shows up here. And then note that ref is just can be rewritten as now the correlated value of the max weight element set function, right? Because when that shows up, well, there's only one set, so there's only one element. So the maximum element is just the element, right? And so when the element is I, then I get just vi hat, right? And so this expected max over the max weight element set function is exactly equal to the ex-ante relaxation revenue. Great. Now let's look at our sequential pricing revenue. Okay, so what's our sequential pricing going to do? Well, to optimize the revenue, sequentially pricing. Again, we're posting prices while supplies last, right? But we get to choose the order the agents show up in. So we should order the agents in decreasing order of price, right? Because then we're most likely going to sell the items at the higher prices. Great. And so if we order each element in decreasing order of price, then if S is the set of agents who are at least their price, then who are we going to sell to? We're going to sell to the one that has the highest price. Well, the prices here are the VI hats. Okay, and so APX is exactly equal to the max weight element set function with distributions given by the marginal probabilities, where the marginal probabilities is the probability your value is at least VI hat. Okay, and so the lemma is that the max weight element set system has correlation gap E over E minus 1. In fact, the max weight element set system is submodular, which is easy to show. And in fact, that would be a great exercise to work on now. So Okay, so between this video and the next video, you can show that the max weight element set function is submodular. And in class, we'll be working on exercise 3, which is the proof of this function. And the approach I recommend taking is the following. Show that it's sufficient to argue this lemma when the distribution f is over singletons. And so instead of looking at general correlated distributions, we're only going to look at correlated distributions over singleton sets, like the one we had here. And then show it's sufficient for uniform weights. Uniform weights meaning the QIs are exactly 1 over n for every I. The marginal probabilities are exactly 1 over n for every I. And then the last step is for uniform weights over singletons, show that the correlation gap is e over a minus 1. And that, in fact, we've already done. That, in fact, was the first proof that we did. This is showing that if we have equal weights and equal values, that the approximation, the gap is e over a minus 1. Great. Okay, so between videos, I recommend showing the max weight element set function is submodular, and in class we'll look at exercise 3. I'm sorry, uniform weights was not the QIs. Uniform weights is the VIs. All right, I'll see you for the next video.